Hello everyone. Good afternoon again. Welcome back to Nirnay IAS English channel. This is Venkatesh, your faculty for geography. I hope you all have completed listening to the last topic which we have discussed. A simple basic understanding about the earth and the universe, things like latitudes, longitudes and all. In this session, we'll go somewhat understanding to the layers of the earth in the interior. We'll understand something about the rocks which are there on the earth's crust. So that's why we have named the topic as the earth's crust, which you can see as the second chapter in our series of basic fundamentals of understanding geography for UPSC civil services. Right? Am I audible to you guys? Let me check. Am I audible to you? Okay. Just a minute. Yeah. Okay. Can any one of you tell me what do you mean by Earth's crust? Can any one of you tell me what do you mean by Earth's crust? Come on, quickly. Okay, fine. If you see, as we have discussed about some of the basics about the Earth and all, now let us understand about the interior distribution. So if you see the interior of the Earth, we all know the interior of the Earth has the structurally is very different. We have the crust, the mantle, the core and all. Why do you think that we need to study about interior of the Earth? What is its significance? What is the significance of learning about something about interior of the Earth? Any one of you? Can you tell me? Can you tell me? What is the significance of understanding about the interior of the Earth? If you start studying about the interior of the Earth, that is when you will understand why do you have volcanoes at certain place, earthquakes at certain place, why do you have certain physical features, something like mountains, something like Deccan traps at certain places and all, will get to know as you study the interior of the Earth. To get to know the physical aspects of a region. You all might have studied about somewhere that there is a possibility that millions of years from now, Africa can be segregated into two components of a continent, right? And a new ocean would be created in the middle of the African continent. That is what you might have heard somewhere. Why do you think that such things happen? Who determines that? The forces which are acting in the interior of the earth. If you study the interior of the earth, you would get to know these aspects. The physical aspects of a region which we are finding at the surface will get to know based on what is happening in the earth's interior. You take a region like Japan. What is Japan prominent for in terms of geographical phenomena? Anyone of you? Can you tell me what is Japan prominent for in terms of geographical phenomena? Come on, quick. Quick. Japan is known for, you take an example like Japan, it is known for earthquakes, right? It is known for volcanoes. And sometimes these earthquakes and volcanoes can trigger even tsunami. Why do you think that Japan is having such kind of various aspects? Why they are having such much impact towards, vulnerability towards various natural disasters emanating from the interior of the earth, the forces? If you understand something about the interior of the earth, it will give you a perspective of these kind of forces. This is the reason why we are studying it. I'll ask you a very simple question. Whenever you talk about earthquakes in India, where do you tend to see about those earthquakes? You tend to see such earthquakes in places like Himalayas, Assam, northeastern states, sections of areas like Gujarat, Bhuj. But you don't talk about huge earthquakes in the peninsular India, no? Why? Peninsular India, the crust of the peninsular India here is having a stable portion, a large stable block, which we call it as craton. That's why we don't have much amount of earthquakes. So what is explaining that? Once again, the interior of the earth. That is the reason why we are learning about it. Am I clear, all of you, on this? Right? So if you see the interior of the earth, it can be divided into structurally into various things, be it the outer layers of the earth, which we call it as the crust, the interior layers, which we can call it as the mantle, and much more deeper ones, which we can call it as the core, which are further divided into outer core, inner core, upper mantle, lower mantle. Right? Now let us try to understand something about the earth's interior. Now, when I have discussed about something about earth's interior, you all have just now understood that crust, core, mantle are the ones which are the divisions of the earth's interior structurally. How do you come to know that this is core, this is earth, this is the core, this is the crust and all? Can you tell me what is the reason for that? How do you come to know about that? Any one of you? How do you know about the interior? What are the sources we have? I'll give you a very simple thing. Volcano is a source. There is a volcano which erupts. The volcano brings up the material which is there inside the earth's surface, that is in the crust, onto the surface. That's what we call it as lava. Magma is in the interior, right? So what is happening? When this material cools down, solidifies, what is happening? We are trying to understand something about the earth's interior. That is there. Then moving further, another thing, mining, drilling. These are also there. You mine a certain region, you are getting information of the earth's interior. That is also true, right? Drilling, you drill certain specialized projects in the Arctic region. We have done it to understand about the earth's interior. These are all what we call it as what? Direct sources. But the thing about these direct sources is they're up to a certain point. Do you really think that the earth's interior is around 6,378 kilometers deeper from the surface? If you need to go into the center of the earth, the depth is around 6,378 kilometers. Are we really getting information to these points? Mining to hardly, it is very few kilometers, 3 to 4 kilometers. Drilling, maybe 8 to 12 kilometers. The first few 100 kilometers, volcano, not even 1,000. Very rarely you will find that. So what is happening? The information which is the sources for the information of the interior of the earth of direct, they're hardly relevant. But you know which are the most the ones which have major impact? If there is one thing which has significant impacted understanding about the earth's interior, are the earthquake waves. There is an earthquake which has happened in the interior of the earth. The point where an earthquake occurs, what do you call that? The energy from the point at which the energy of the earthquake has been released. What do you call that? Anyone? Can I call it as focus, or should we call it as the epicenter? Focus or epicenter? Arjun, it is not epicenter. Epicenter is on the surface. Say, if this is the Earth's interior, if an earthquake has occurred here, the point where an earthquake occurs is what we call it as focus. From the focus, the point where an earthquake, as the energy waves travel, which will reach for the first time here, is what we call it as epicenter. These earthquake waves, because the energy is traveling in the form of waves, that waves have helped us in understanding. There are two types of earthquake waves. We call it as body waves and surface waves. Body waves, surface waves. Body waves are of two types: primary waves, secondary waves. For a while, you can ignore the surface waves. Understand something about the body waves. The earthquake waves which are traveling in the interior of the earth are called as body waves and surface waves. In these body waves and surface waves, right? In this surface waves, in this earthquake waves of body waves and body waves, the primary and the secondary, they are traveling. The energy is traveling. But the thing is, these body waves, we are not observing beyond a certain point. So let me show you a picture. If you see the earthquake waves, the primary wave patterns, they are not being reported at a certain place. The secondary waves are not reported beyond a certain point. Now we all know some of the basic fundamental things about a wave. As a kid, we all have done this experiment. There is a bucket of water, we have a torchlight, we have put the torchlight, we have angled it towards the bucket of water. We have seen that the light waves have significantly changed their direction at the point of change in the medium from air towards the water. That is what we call it as refraction. Do you remember it, all of you? Refraction. In a similar way, the primary waves, they change their direction. So what is that? Primary wave change their direction when there is change in medium. Not just direction, but also the speeds, velocity. There is a change. Similarly, secondary waves, they don't travel in liquid medium. So what happened is, if an earthquake has occurred here, and from here the energy waves have started traveling, after a certain point, there were no earthquakes which were reported, say beyond 103 degrees. So there are we have all the seismic equipments, seismographs, which will measure the earthquake waves across the world, at the surface. Whenever an earthquake occurs exactly at a certain angle, 103 degrees, there were no earthquake waves. So this is what we call it as shadow zone. Whereas primary waves, the shadow zone is smaller, is only a smaller 103 to 145, 150 degrees. Simple reason, exactly at around 2880 kilometers into the center of into the interior, there are bending. Why are they bending? They are changing from the mantle into the core, which is liquid medium. Outer core is liquid, inner core is solid. Because of that, you have observed that there were no earthquake waves reported for primary waves between 103 to 145 degrees, and for secondary waves beyond 103 degrees. Simple reason why the S waves could not travel here is outer core is liquid. Outer core is liquid, but these waves like primary do travel. This have helped us in understanding that, okay, there is a differential in the medium of the earth, in the interior of the earth, and through the further studies, we have categorized that as something called as mantle, something called as core, something called as crust. Have you got my point, all of you? You clearly see here, there is a primary wave. The primary wave is consistent more or less here. This is the crust of the earth. Then there is some subtle variation, which is the asthenosphere, the magma layer. Then there is a consistency, which is the mantle. Suddenly there is a change in the velocity of the primary wave. This is once again the outer core. This is liquid. Once again, this is solid, similar velocities. So what is happening here? We are observing that the waves are having a continuous velocities at a certain pattern throughout the interior of the earth, indicating that the density is probably one and the same. The material could be one and the same. So how do you ascertain that crust, mantle and core? Based on the earthquake waves. So simply remember, S waves don't travel in liquid. Primary waves change their direction and the speed varies. So only for S waves. With these things, based on the direction and the velocities of the waves, velocity of seismic waves, we got to know something about the interior of the earth. That first layer is what we call it as the crust, the outermost layer. Outermost layer of the earth's surface is what we call it as crust. Are you following me, all of you? Any doubts you have? Any doubts? And this outermost layer, okay, let me continue then. This outermost layer of the crust is what we call it as the thinnest layer. It is very, very thin. By the way, it is also very, very brittle. Brittle is which can be easily broken. Very much easily broken. And you see, how do you think that the crust is there? Imagine this is the land. And here we have the ocean. The land continental crust comprises of materials like silicon, aluminum and all. That's why it is called a Sia layer, where the density, this is the continent, this is the ocean surface. The continental crust comprises of lighter elements like silicon and aluminum. That's where the density is around 2.7 grams per centimeter cube. Whereas the beyond the Sia layer subsurface, this is entirely a 𝐸𝐴 layer, silicon magnesium, which is slightly heavier denser at 3 grams per centimeter cube. In other words, I can say that, so for a simple understanding, I can say that Cr layer is floating in the asthenosphere. Cr layer is floating in the asthenosphere. This is what is happening about the crust. So simply remember it as outer crust, the crust, outermost layer is the crust, thinnest layer. It is very, very brittle, easily broken. And the continental crust is the lighter one comprising of silicon and aluminium. And the heavier one is silicon and magnesium, which is the oceanic crust, which is denser. Right. You can also see here, this is the crust. This is the continental crust, Cl. This is the oceanic crust, which is 𝐶𝐸MA. Okay, you can see here, oceanic crust, this is 𝐶𝐸MA. This would be the Cr layer. Then, if you see the depth, at the oceanic crust, the depth is around, just around 5 kilometers. For a continent, the average I can consider as 30 kilometers, and in the mountains, it will go as much as 70 kilometers. You can see here, this is the seabed, this is the crust, just few kilometers. This is a huge area. 70 kilometers in the ocean, in the mountains. Simply land, you can remember 30, ocean 5. That's it. Then we'll go to the next point, mantle. What is upper portion of mantle called as? Upper portion of mantle, what is it called it as? Anyone? Upper portion of mantle is what we call it as asthenosphere, which is semi-viscous, semi-solid. Semi-viscous, semi-solid. That is the asthenosphere, the magma layer. Until here, I can consider it as crust plus upper portions of mantle. That is what we call it as lithosphere. What is this? Lithosphere. Rock sphere. Let me see some comments. Until here, I can consider it as right. Lithosphere, rock sphere. That rock sphere is the crust and the upper portions of the mantle. Right? Then the density of the mantle, it will keeps on increasing to 5 grams per centimeter cube, which is much more denser density. And remember, among the Earth's among the entire interior of the Earth, volume-wise, mantle is very, very dominant. Almost 83% of the Earth's interior is of mantle layer. And this stays until 2,880 kilometers. After 2,880 kilometers, that is when we have something called as a core. So you can see it here. This is the center, which is around 6,370 kilometers. You can remember as 6370 for simple understanding. The mountains, the oceans which we have and all, this is the crust. The first few kilometers, this is the entire mantle until 2,880 kilometers. Then we have the core. Core is once again divided into outer core, inner core. Outer core is liquid, right? For example, remember outer core liquid, inner core solid. Both comprise of materials like nickel, iron. That's why we call it as knife layer, nickel and ferrous. Nickel and ferrous, knife layer, and the core's density also tends to increase until 13 grams per centimeter cube. So as you move from the surface into the interior, because of the heavy weight and all, we all tend to see maximum. We all tend to see something about much more heavy density, 13 grams per centimeter cube. Right. Am I clear, all of you? Are you able to follow me? Any doubts so far? Then try to answer these questions. Answer this. Last 30 seconds. Arjun says option 2. Okay. That means for you 1 and 3 are correct. Others, can you answer? Quickly. Okay. Done. Time out. The answer is correct. Option 2. Arjun, you are right. If you see, with reference to structure of the earth, consider the following statements. The continental crust is thicker in the areas of major mountain systems. Yes, we have seen it 70 kilometers. The upper portions of the crust is asthenosphere. No, mantle is asthenosphere. So this is wrong. The outer core is in a liquid state while the inner core is a solid state. Yes. Answer is 1 and 3. Right? So that is what, very simple, basic. You should have got it right. Let us see the next question now. One minute time. Okay, last 30 seconds. Last 30 seconds. I want you to participate. Kindly participate in the live chat. Answer the question. Okay, Arjun says 3. Let's see. Yeah, time out. Now you see. The shadow zone of S waves. We have seen that shadow zone of S waves is much more bigger, beyond 103 degrees, whereas the shadow waves of primary waves is smaller. The answer is shadow zone of S waves is smaller than P waves. That's what the statement says, which is wrong. The P waves are similar to sound waves. They change their direction, velocities with the change in the medium. True. So that's why the answer is 1 only. Right? So that is about some of the questions. We'll go to the next point. Rocks. Rocks. Can any one of you tell me what is the difference between element rocks, minerals. Element, rocks, minerals. Any one of you, can you tell me the difference? Quick. Hello, Hemant. Good evening. Hello, Hemant. Okay, can you answer this question? What is the difference between element, rock, mineral? Okay, let me explain. You take a certain rock, granitic rock. A granitic rock is made up of various minerals. Combinations of minerals is what we call it as rocks. Rocks are aggregate of minerals. And the minerals are combinations of multiple elements. So you have elements. Rocks are nothing but what? Aggregate of minerals. Rocks are simply aggregate of minerals. This aggregate of minerals combinations, which are, you will not find rock in a simple form. They are always found in the ores. We'll say that, for example, mineral, we tend to say they are found in the ores, right? So they are aggregate. The rocks are aggregate of minerals. Thus minerals will be having that things which we use it. Once you use the minerals, whatever the elements which we can use it, you can extract out of the rocks. That's why we call it as ore, no? For example, what is the ore which we call it as iron ore? Anyone? Can you tell me? Hello, Dilip. Hello, Hemant, Arjun. Can you tell me what is the ore which we call it as something about the ore of iron ore? Hematite, magnetite. These are some of the ores, no? What do they have? You will not have the entire ore comprising about the mineral called as iron ore, no? Iron, no? They are always available in some combinations, right? That is what the things are. So we have elements across the Earth's crust. These elements are formed together, which are called as minerals. Minerals are not easily found. They are found in combinations with other rocks. That's why we'll call it as rocks as aggregate of minerals. That is there. With this, let us move forward. So simply remember rocks as aggregate of minerals. These aggregate of minerals rocks, we can divide them into three types. Three types. Yes, Hemant, you are right. Hematite, you are right. So rocks are of three types. What are they? Igneous rock, sedimentary rock, metamorphic rock. So igneous. What is igneous? So you see things like granite, igneous rock, things like gabbro, basalt, andesite, all these are igneous rocks. What are they? Igneous rocks are rocks found out of fire. Rocks which are formed out of fire. That is solidification and cooling down of magma. Or we can also say lava on the Earth's surface. Once a volcano erupts, or for that matter volcano, it provides some kind of magma in the interior and it erupts onto the Earth's surface as lava. It solidifies and cools down. That cooling down nature, once it happens, are what we call it as igneous rocks. Igneous, that's why they're called as fire rocks. And these are the base rocks of the world. That's why we can also call them as primary rocks. Primary rocks. I'll give an example here. You see here. You see here. There is inside the Earth's crust. We have seen that there is mantle. Upper portion of the mantle is asthenosphere, magma layer. From the magma layer, volcano erupts. That volcano can reach the surface, cannot reach the surface. It depends on the pressure of the magma force. It depends on the rock nature here and so many combinations. So sometimes what happens is, if this is the magma layer, a magma chamber, and this is the Earth's surface, sometimes a magma chamber in the Earth's surface will create a variety of structures like this, whatever. And sometimes it can create a volcano, as you are imagining. A volcano can be there. The eruption is there. This is what the lava, this is magma. So when the lava and the magma cools down, be it the interior of the Earth, be in the outside of the Earth, we call them as igneous rocks. For example, if they are cooling down inside the Earth's surface, they are called as intrusive rocks. Intrusive rocks. If they are cooling outside the Earth's surface, we are calling it as extrusive rocks. Can you tell me which one will be cooling down faster? Yes, Dilip. You can say various landforms, laccolith, bacoliths, right? Dikes, sills, okay, all these things. Good. Yes, various things. For example, because these are the igneous rocks are the ones which takes so much amount of time to cool down, especially the intrusive rocks, because they are inside the Earth's surface, the heat is quite high. So the time taken to cool down, the time taken to solidify, and also the time taken for crystallization to occur, they will take more time. When the crystallization is having more time, crystallization for it to occur takes more time, that is when we will find that we tend to have long grains. Relatively, these are small grains. Because of this long grains, more time taken to cool down and all, they have become very, very rock solid. We use the word rock solid, no? Right? What do you mean by rock solid? Difficult to erode, difficult to break down. So that's one such rock is granitic rock. That's why granite we used in the construction industry. For example, you take the Lord Ram's statue, which you have kept at Ayodhya. If I am not, excuse me, if I am not wrong, that statue is prepared out of a granitic rock from Karnataka. Granitic rock from Karnataka. Right? So these rocks are used in the construction industry. They're used for prepare for statues and all. The political statues and all we prepare out of the granitic rock. So that's why they are quite long lasting, not easily eroding. You will not find the rock exposing to the sun's heat, rainfall and all. It will not break down very, very easily. So that is the intrusive rocks which are having long time for solidification. It will take long time. That's why there is good crystallization. Good crystallization is the reason why long grains, which makes it very, very strong. That is what we can say it as, something in a simple layman's words, rock solid. Right? So remember some of the basics of the igneous rocks. Then some examples. We need to give some examples. Granitic rock, andesitic rock, Andes mountain formed out of the volcanism and folding. Basalt is a volcanic province. Flood basalts, for example, you all might have heard as part of your childhood. Deccan Plateau is formed of basaltic lava sheet. Basaltic lava sheet. There are certain volcanoes, instead of spread, they tend to spread outwards. These volcanoes, they tend to what? They spread outwards. We don't find this basaltic lava sheet forming like a cone. They tend to spread and they're going to travel for longer distances. So that's why we call it as basaltic lava sheet. There are also one type of dark colored thing. That's why you can see the color dark. Basalt is one such igneous rock. Wherever across the world, we all tend to see that they are formed out of igneous rocks only. Then comes the sedimentary rock. Can you tell me what is a sedimentary rock? Dilip, Hemant, Arjun, can you tell me what is a sedimentary rock? Can you tell me what is sedimentary rock? Come on, quickly. No? Sediments of a river, says Dilip. Who is this? Dilip? Yeah. Sediments of a river. Okay. I think you are fairly confusing. Yeah, I can say you are not wrong, very close to it. See, the rocks which are formed out of accumulation and over a period of time compaction of weathered material or sediments, accumulation and compaction of sediments is what we call it as sedimentary rocks. We can fairly say that the rivers are eroding that. As the rivers are eroding the mountains and all, they are catching so much amount of load of the load of the river is nothing but sediments which they have eroded. Those sediments, as the rivers have taken away and dumped at a certain place, river is only one type of a source of sedimentary rock which the material is coming up. Similarly, you'll find wind. There are so many other things. That's why sedimentary rocks are very different from sediments of a river. But sediments of a river create sedimentary rocks, right? For example, you have wind. In the deserts also, winds will be eroding some of the rocky landscapes of desert. The winds carry the dust, they dump. That is also a sedimentary rock sometimes. Right? Did you get my point, Dilip? The differentiation between the sedimentary rocks and rivers carrying sediments, right? So whatever the nature which you have, the erosion which happens, the weathering which happens, and the material is transported, that accumulation and compaction of sediments is what we call it as sedimentary rock. Okay? Remember, whatever the igneous rock, or for that matter, the sedimentary rock itself, or a metamorphic rock, any rock that is subjected to breakdown, that is subjected to breakdown. Any rock would be breaking down, disintegrate. You are not taking a hammer and breaking it. The rock will break apart on its own. That breaking apart is what we call it as weathering. That weathering can occur simply, fastly, quickly, or sometimes takes thousands of years. It all depends on the force of the weathering process and also the strength of the rock. Some rocks are very, very strong. Some rocks are very, very soft. But one thing is common. In millions of years, everything is constant. Nothing is constant. Change is the only constant. Everything changes. Maybe not now, but in millions of years. Right? So that is what I can say. Any rock would be weathered, eroded. They would be transported by a certain agent, by a wind, by a river, as you have said. And then finally, whatever the material which will be dumped, deposited at a certain place, at that deposition, you find compaction and accumulation. That compaction and accumulation which happens together forms a sedimentary rock. Right? So they have all the material deposits. That's where you find they have layers. Why do you think that they have the layers? Because each layer discusses about one type of sedimentation process at one time. One type and one at one time. So that is the things. That's why they tend to have fossils. Not just that. I would say sedimentary rocks are like scrapbooks. We all have the scrapbook, right? Which record all the past events. So these are the scrapbooks of the earth. They record all the past events. Understanding about the sedimentary rocks will give you an understanding about geological history of the earth. Right? So they record all past events. All the geological events you can get to know through the sedimentary rocks. And that is where here, because of the organic matter also can accumulate here, they contain fossils. Right? Am I right, Dilip? Are you following me? Now you see, these sedimentary rocks, they are of three types. For example, organic, that accumulation can happen when an organic of the organic matter as well, right? If the biological matter is more dumped, say you can say something like a rock called coal can be created. So the sedimentation accumulation can happen of the organic matter like coal, right? Limestone is one such example I can also give. What if the things occur on a chemical basis? Chemical accumulation. Chemical accumulation. So maybe the precipitation, maybe the molecule, the mineral precipitation, we can say so, whatever the things are. From the things, you take something like rock salt, gypsum. Chemically, you are weathering down and dumping. That is also one type of a sedimentary rock. Or fragments of the earth crust can also be dumped, mechanically formed. Say like sandstone. That is also one type of a sedimentary rock. That is also one type of a sedimentary rock. You can remember the examples. Coal, just now I told you, sandstone, rock salt, gypsum are some of the examples. Limestone. By the way, have you heard about this word conglomerate? Conglomerate. In the Shivaliks, we tend to find significant conglomerate rocks. The rivers which have eroded the Himalayas in the upper portions of the Himalayas, they have dumped all the sediments on the Shivalik area, and these Shivaliks are nothing but conglomerate rocks. Conglomerate means aggregate of rocks, no? Conglomerate. When multiple companies come together, conglomerate we tend to say accumulation. So I can say that Shivalik rocks are also conglomerate rocks. Okay. What happened, Dilip? Not able to understand? Didn't get the point? conglomerate rocks we tend to find in the Shivaliks. Shivaliks are the outer Himalayas. So the rivers which are eroding the Himalayas in the upper portions, greater Himalayas, lesser Himalayas and all, they will bring the sediments and dump here. These sediments have accumulated over a period of time. That accumulated conglomerate rock. You can see that's where there are multiple structures. That is the sedimentary rock. Then we'll have the next one, the metamorphic rock. Now, you have any pre-existing rock. It could be igneous rock. It could be the sedimentary rock. It could be, by the way, metamorphic rock itself. Any pre-existing rock under the influence of pressure, temperature, volume, if changes its form, we call it as metamorphic rock. Metamorphism means change. So imagine there is a folding process. For example, you take, do you remember something called, there was a Tethys Sea, ancient Tethys Sea? When this Tethys Sea was moving as part of the plate movement, Indian plate, along with moving towards the Eurasia, the Tethys Sea sediments, as it hit the Eurasian coast, when there is some two continents are hitting each other, there is a folding structure which has happened, which we call as the present Himalayas. No, Himalayas are fold mountains. When these fold mountains have happened, these fold mountains are a product of, you know what? The fold mountains are a product of the complete folding nature of the Earth's crust. This is nothing but influence of pressure, impact of temperature. So the ancient Tethys Sea sediments have been changed. So any pre-existing rock, be it the various geomorphic processes, if they come very close to a certain thing like magma and all, for example, you can see this picture. Imagine there was no volcano at a certain point. Slowly this magma chamber was created and all. That means these surrounding areas have come in contact with the magma. What happens? Under the influence of temperature, the rock nature would change. Imagine this block of the earth has been compressed. Then also they will be changing. So any pre-existing rock under the influence of pressure, temperature, if they change, we call it as metamorphic rock. That is how a hard igneous rock like granitic rock can change into gneiss. Coal can change into graphite. Shale can turn into schist. Shale can turn into schist. If you see India's peninsular India, which got separated out of the Gondwana land as part of the continental drift, all these combinations, that's why we say peninsular India is a combination of granitic gneiss and schist. What is that, my dear? Granitic gneiss and schist. Why? All this indicates that they are found in combination. There is a granite rock. That granite rock has been metamorphized because of the forces of the interior of the earth since so many years. Right? That led to the gneiss, and a combination of shale rock is also led to schist. Right? Are you following me, all of you? Are you following me? Okay. Dilip is asking how volume is involved in metamorphism process. Okay. How do you explain? Imagine the rock is in the deep interior. Maybe a rock which instead of here is now here. There is a pressure of this entire upper portions on it, no? The pore spaces in the rock, they tend to be impacted by that thing. As the pore spaces of the rocks gets compacted and all, over a period of time, the rock might change its nature. So, in other words, that volume will be providing the pressure, right? Lithospheric pressure. Lithosphere is rock. That rock pressure outside of the rocks which are above us, they create a significant impact in the interior of the earth, and that can lead to metamorphism. Now you got my point? Now you got my point? Dilip? Volume? See, the pressure here, which is pushing on the rocks, definitely that will change the volume of the rock, and the grain alignment will be realigned. The recrystallization also would be happening. That recrystallization on will lead to a new structure. That is what is metamorphism. Right. I hope you got it now, Dilip. Right. Good. Right then, if you see, my dear, in the last class we have discussed these topics. If you need more such information and all, you can get into my Telegram channel, right? You can simply scan the QR code, and for you to have a comprehensive course of the entire subjects of UPSC civil services, both for prelims, mains, interview and all, you can go back to you can use my code Venkatesh. Using the code Venkatesh, you can subscribe to the complete course, which will give you an organized, complete understanding of all the topics needed for your civil services exam, right? So you can use the code Venkatesh, and for more such information and all, you can scan the QR code. That's it then. Okay. I hope you all have understood the entire things about the rocks, about the earth's crust and all. That's it for today then. Until we meet next time, I hope you have a good time. Enjoy the learning process and all. And we will once again come back with a new topic tomorrow in the next week, and we will discuss. Until then, take care. Goodbye. Enjoy the process. Have a smile on your face. Thank you. Thank you, Dilip. Thank you, Hemant. Thank you, Arjun. See you again next week. Thank you.